Well, we are going to get started. Today we are going to do the last section of Chapter 8, Section 8.3 on estimating a population mean. This is going to be very similar to the work we did last week with estimating a population proportion. The formulas are just going to change a little bit. And obviously we're focusing on means rather than proportions. All right. So we've got a presentation today with some examples in it, and then I have a couple other examples that I'm going to do after the presentation is over. I recommend that you have something to take notes with. You're not going to need to write down a ton of notes today, as far as like, you can try to copy some of the stuff from the slides, but it's not absolutely necessary. There's a few formulas and some conditions and things that you're going to want to record so that you can use them later. But a lot of the stuff in here is just kind of trying to show you how these things are related to things we've done previously. All right. So that's how that's going to go. I hope you guys all had a great weekend and that Monday went well and that you're feeling good. And if you're not, I hope it gets better. So we're going to get this thing going. Gonna share my screen. And as usual, if you have questions, if you need me to slow down, if you need me to clarify something, please raise your hand, let me know. Type it in the chat, unmute your mic and shout at me. Those all work. All right, so here we are, Chapter 8, Estimating with Confidence. We're doing Section 8.3, Estimating a Population Mean. All right, so today we're going to look at all of these things. We're going to learn how to state and check the random 10% and normal large sample conditions for constructing a confidence interval for a population mean. Explain how the t-distributions are different from the standard normal distribution and why it is necessary to use a t-distribution when calculating a confidence interval for a population mean. We need to determine critical values for calculating a C % confidence interval for a population mean using a table or technology. We want to construct and interpret a confidence interval for a population mean. We need to determine the sample size required to obtain a C % confidence interval for a population mean with a specified margin of error. All right, so those are the goals for today. Hopefully we'll get to see all of them, which not hopefully we will. So first, when sigma is unknown, when our standard deviation for a population is not known, right, we use t-distributions. When the sampling distribution of x bar is close to normal, we can find probabilities involving x bar by standardizing, right? And this is what we've seen previously when dealing with our sampling distributions. We have z equals x bar minus mu divided by sigma divided by square root of n. And this is familiar because it goes from our sampling distribution and it standardizes to our standard normal curve to where we have a mean of 0, standard deviation of 1, and we can then treat this as a normal distribution and calculate probabilities and proportions and all that fun stuff. When we don't know sigma, we can estimate it using the sample standard deviation S sub x. What happens when we standardize? What is this thing now equal to, because it's not z anymore? We get a t-distribution. When we standardize based on the sample standard deviation S sub x, our statistic has a new distribution called a t-distribution. It has a different shape than the standard normal curve. It is symmetric with a single peak at 0. However, it has much more area in the tails. Right, so we get this comparison here. This is our t distribution. Okay, x bar minus mu divided by s sub x divided by square root of n. The standardized score is z, x bar minus mu divided by sigma divided by square root of n. Right? The only difference is this sigma and S sub x, but we notice that the t distribution is much more spread out, right? A little bit squattier, right? A lot more variance. The z-score is much taller and much less varied. And this is what it means by there's more area in the tails as we go off to the right or to the left. There's a lot more left on those edges than down here. Like any standardized statistic, t tells us how far x bar is from its mean mu in standard deviation units. There's a different t distribution for each sample size specified by its degrees of freedom. Why it's called degrees of freedom, I'm not entirely sure. That's just what they call it. All right. And how we determine the degrees of freedom, we will see in just a moment. Does anyone have any questions or need clarifications so far? Or does anyone need time to write anything down? When we perform inference about a population mean mu using a t distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size n, making the degrees of freedom equal to n minus 1. So that's how we determine degrees of freedom. We will write the t distribution with n minus 1 degrees of freedom as t n minus 1. So you don't need to write this box of stuff down. This is showing that same t distribution calculation we just saw, and it's based on substituting S sub x, the sample standard deviation, for standard deviation of the population. All right. So what is the t distribution? What does it look like? That's what we're going to see next. So when comparing the density curves of the standard normal distribution and t distribution, several facts are apparent. And here we've got a little figure. The bottom and the top curve, right? The most narrow and tallest curve is our standard normal curve. The kind of shortest and then most spread out is 2 degrees of freedom t distribution. And then that one that's kind of in the middle, that is a t distribution with 9 degrees of freedom. All right, so you can see that they're very similarly shaped, right? They're not exactly the same, but similar. They're symmetric, centered at 0. That kind of works out. The density curves of the t distributions are similar in shape to the standard normal curve. The spread of the t distributions is a bit greater than that of the standard normal distribution. The t distributions have more probability in the tails and less in the center than does the standard normal. And as the degrees of freedom increase, meaning our sample size is getting larger, the t density curve approaches the standard normal curve ever more closely. Essentially, this is directly related to the fact that as we get a larger sample, we get less variance, right? The spread of our distribution becomes smaller. Smaller sample size, more variance, right? And so that's why these t distributions for very small degrees of freedom, meaning you had a very small sample, is more fat, more spread out, squattier than when you start getting larger degrees of freedom, implying a larger sample. Haha. All right. So here we go. Here's our example. We need to find the critical value t star, and we find our t distribution and our t star values, which is same as we use the z-score for proportions. And then we called it z star after using table A. We're using table B, which is a one-page table, which is kind of nice, to find critical t star values. Okay, so what critical value t star from table B should be used in constructing a confidence interval for the population mean in each of the following settings. So first one is we have a 95% confidence interval based on an SRS of size n equals 12. So in our solution here, on table B, we consult the row corresponding to the degree of freedom equaling 12 minus 1, which is 11. All right, and what that looks like here on table B is we find the degree of freedom 11 on that left-hand column, and then we find the confidence level C along the bottom row of the table. On the bottom row of the table, it just lists a bunch of confidence levels. It starts at 50% and works its way to 99.9%. And this table is part of the forms and tables that you will be provided on the AP exam. When we find the intersection between that row and that column, we get 2.201. Right. And again, this is describing that. We move across that row to the entry that is directly above 95% confidence level on the bottom of the chart. The desired critical value is T star equals 2.201. So this would be the critical value we would then use when calculating our interval for a 95% confidence interval. We'll see an example of this. All right, here's another scenario. We have a 90% confidence interval from a random sample of 48 observations. Right, with 48 observations, we want to find the T star critical value for the degree of freedom equaling 48 minus 1 is 47, and 90% confidence. So again, we consult table B. But notice there is no degree of freedom equaling 47 in table B. It's not a typo. It's not like we were just trying to save space and we started counting by tens. It lists every degree of freedom from 1 to, I think, goes up to 30, and then it starts skipping, and then the skips become bigger later. And so we play by Price is Right rules. You want to get as close as you can without going over. So because 47 is the degree of freedom we want, we cannot go up to 50, even though we're closer to 50. We round back down to 40 to be a little more conservative. And so the corresponding critical value is T star equals 1.684. Is there anything I can clarify on how to use table B here? Okay. All right, so we have conditions for estimating mu. As with proportions, you should check some important conditions before constructing a confidence interval for a population mean. Right? And these are the conditions we're supposed to check. These you're going to want to write down. Very similar to what we did for proportions. We're just essentially switching the last one to apply to means. We still need to check for randomness. The data has to come from a well-designed random sample or randomized experiment. Right? We need to check the 10% condition when sampling without replacement, which most of our sampling will be without replacement, especially if we're dealing with people or live things. We need to check that n, our sample size, is less than or equal to 1 over 10, 1/10 or 10% of the actual population. And lastly, we check the normal large sample. Population has a normal distribution or the sample size is large and being greater than or equal to 30. All right. So if the parent population is normal, we're good. All right. If the sample size is large enough, right, the central limit theorem is we have that, then n is greater than or equal to 30, we're good. Otherwise, if the population distribution has unknown shape and n is less than 30, we need to make the graph of our sample, like a box plot, dot plot, something, so that we can see what it looks like. What's the shape? Okay. And we need to assess its normality. we cannot use T procedures if the graph shows strong skewness or outliers. If we don't really see any skew or nothing like crazy, and there doesn't appear to be any outliers, we're probably good to use the T distribution in T procedures. Otherwise, we're done. We can't use it. All right. And from what I've been told and what I've read, if you're being asked to assess the normality, like this is the option you're at, it will be apparent that it's either just doesn't really have a skew, it doesn't look like there's outliers, or it's going to be like super obvious that it's skewed and that there might be outliers. Okay. So these are our conditions. When constructing a confidence interval here, when the conditions for inference are satisfied, the sampling distribution for X bar has roughly a normal distribution. Because we don't know sigma, we estimate it by the sample standard deviation S sub X. Right, the standard error of the sample mean X bar is S sub X divided by the square root of N. And so this is called, if things want to cooperate with me, which they don't, the one sample T interval for a population mean. Right, the one sample T interval for a population mean is similar in both reasoning and computational detail to the one sample Z interval for a population proportion, which we use to do inference for population proportion. This is for inference on population means. We have the one sample T interval for a population mean when the conditions are met. A C% confidence interval for the unknown mean mu is X bar plus or minus T star times S sub X divided by square root of N, where T star is the critical value for the T n minus 1 distribution with C% of its area between negative T star and T star. This formula you're going to want to have recorded somewhere and get used to using for this inference method, right? Making an inference about a population mean. All right. So, can you please raise your hand if you need a moment to write this down? Alrighty. Let's continue. So we're going to do an example. So we're going to use this new one sample T interval for mu. Environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides, or NOx. Researchers collected data on the NOx levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675, and the standard deviation was 0.3332. We want to construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. And we're going to use our 4-step process: state, plan, do, conclude, to make sure we cover all the bases. So number 1, state. This is what we're going to do. We want to estimate the true mean amount mu of NOx emitted by all light-duty engines of this type at a 95% confidence level. That's what we want to do. That's our goal. Our plan is, if the conditions are met, we should use the one sample T interval to estimate mu. Part of the plan is checking the conditions. Right? Was this a random sample? And well, yes, the data came from a random sample of 40 engines. So we're good on the random sample. 10% condition, we are sampling without replacement, so we need to assume that there are at least 400 light-duty engines of this type. That's a fair assumption, considering there's millions of cars. We're bound to have at least 400 light-duty engines. And the large sample condition, right? We don't know if the population distribution of NOx emissions is normal. However, because the sample size is large, n equals 40, which is greater than 30, we should be safe using a T distribution. All right, so we've done our first 2 steps of the 4-step process. We stated what we wanted to do, and we've reviewed our plan and checked our conditions. Now we got to do some math. From the information given, x bar equals 1.2675 grams per mile, and S sub x, right, the standard deviation for our sample, is 0.3332 grams per mile. To find the critical value t star, we use the distribution. We use the t distribution with degrees of freedom 40 minus 1 equals 39. Unfortunately, there is no row corresponding to 39 degrees of freedom in table B. We can't pretend we have a larger sample size than we actually do, so we use the more conservative degree of freedom equaling 30. Right, and we're at 95% confidence. That gives us a 2.042 t star value, or critical value. Anyone have any questions so far? So then we do our calculation to get our interval. We have x bar plus or minus t star times s sub x divided by square root of n, which is equal to 1.2675 plus or minus 2.042 times 0.3332 divided by square root of 40, which is equal to 1.2675 plus or minus 0.1076. And we have the interval from 1.1599 to 1.3751. Now that we've done all the math, we have our interval for our 95% confidence level. We make our conclusion. We are 95% confident that the interval from 1.1599 to 1.3751 grams per mile captures the true mean level of nitrogen oxides emitted by this type of light-duty engine. And that's the problem. That's our example. Is there anything I can clarify? So just like we were able to do with proportions, there are times where we need to choose our sample size before collecting our samples and getting data. Right, we determine a sample size for a desired margin of error when estimating a mean in much the same way we did when estimating a proportion. All right, choosing sample size for a desired margin of error when estimating mu. Again, this is something you might want to write down. To determine the sample size n that will yield a level C confidence interval for a population mean with a specified margin of error ME, we get a reasonable value for the population standard deviation sigma from an earlier or pilot study. That's the only option. We need to have some value for sigma, and the only option is having some reasonable value from a previous or pilot study. There's no like default to some standard deviation. We can do that with proportions, right? If we don't have some reasonable value from an earlier pilot study with a proportion, we just go, okay, well, let's use 0.5. For means, we don't have that luxury. We either have something or we don't. If we don't, we're kind of stuck. We're done. All right, we need to find the critical value z star. This is not a typo. We're using z star again. From a standard normal curve for confidence level C, we set the expression for the margin of error to be less than or equal to the margin of error and solve for n. So same strategy as we used for proportions. We're now just using the margin of error portion of our interval calculation from a mean by using z star, sigma, square root of n, less than or equal to margin of error. Does anyone need a moment to write this down? So here's our example on this one. Researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter, mg per dl, of the true value of mu at a 95% confidence level. A previous study involving this variety of monkey suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. Problem. Obtaining monkeys is time-consuming and expensive, so the researchers want to know the minimum number of monkeys they will need to generate a satisfactory estimate. So we're going to set it up. So for our solution we use for 95% confidence, we have a z-star of 1.96. Again, this is a result that we've used several times now. 95% confidence interval is very common. So we have z-star equals 1.96. We'll use sigma equaling 5 as our best guess for the standard deviation of the monkey's cholesterol level. That's based on that previous study. We set the expression for the margin of error to be at most 1 and solve for n. So we got to solve this inequality. So we get our margin of error formula, so to say, over here. 1.96 times 5 divided by square root of n is less than or equal to 1. Multiply both sides by square root of n and divide each side by 1. And we then square both sides to get rid of the square root sign here, and we get 96.04 is less than or equal to n. Because 96 monkeys would be a lot of monkeys, would give a slightly larger margin of error than desired, the researchers would need 97 monkeys to estimate the cholesterol levels to their satisfaction. And again, this is due to this being an inequality. I cannot use any value less than 96.04, which 96 is less than that, so it's not a viable option. I must go up. So we go to 97. Is there anything I can clarify about this problem? Okie dokie. That's the end of the presentation. So now we're going to look at some examples. Let's hope this stuff works. All right. So here we go. We're going to look at a couple more examples, one with constructing and interpreting a confidence interval, and then deciding whether or not that supports a claim, and then finding a minimum sample size. All right, so here's our first example. We have bone loss by nursing mothers. Right? Breastfeeding mothers secrete calcium into their milk. Some of the calcium may come from their bones, so mothers may lose bone mineral. Researchers measured the percent change in bone mineral content, BMC, of the spines of 47 randomly selected mothers. That's kind of something we're going to need. During 3 months of breastfeeding, the mean change in BMC was negative 3.587%, and the standard deviation was 2.506%. We need to construct and interpret a 99% confidence interval to estimate the mean percent change in BMC in the population. All right, so this is what we're working on. So we're going to use our 4-step process here, and we'll start with stating what we're going to do. All right. And we want to estimate the true mean percent change mu in BMC in the population. With a 99% confidence level. That's what we're working towards. That's what we want to do. So we've stated this. This is our goal. All right. Next, we plan. So if conditions are met, we're going to use a 1 sample t interval to estimate mu. All right. And we can't move on until we check our conditions. We got random. Well, the mothers were randomly selected. Cool. Random is taken care of. 10%. We can assume that 47 is less than 10% of the population of breastfeeding mothers. And that's just a fair assumption to make based on, like, well, in the US alone, there's probably more than 470 breastfeeding mothers at any given time. Okay. Then we have our large sample condition, right? Since 47 is greater than 30, this condition is met. That's kind of an easy one. It's just looking at the numbers. We're at the sample size larger than 30, so we're good to go. Now we move on to our do step. All right, now getting to our calculation, we need to have, let's kind of list out what we have here. So we know that our X bar, right, our sample mean was negative 3.587%. And the sample standard deviation is 2.506%. Right, we need that. And the other piece of this we need, right? We know n, it's 47. Right? The degree of freedom, because we're going to need to use that on table B below here, is 47 minus 1, it's 46. And we need to find T star, and this is at a 99%. It's terrible looking, 99%. There. All right, so this is where we're going. We need this last piece of information using table B. So we're going to look at table B here. Again, notice that there's the interior of the table, which is the T star values that we're going to use. We have the degrees of freedom down the left-hand column. right? Confidence levels along the bottom. And then we have the tail probability along the top. We're not really using this tail probability right now, so just don't stress on that right now. So we're going to find, right, 46 under degrees of freedom. But again, we don't have 46. And playing by Price is Right rules, we have to go back down to 40 because I can't use 50. 50 goes over. So we're going to need 40 here. And I'm just going to kind of like highlight all the way across so we can find where it intersects with the 99%. 99% is right down here at the bottom. And so we'll follow this guy up here. Right? And we intersect right here at 2.704. So that is the T star value that we're going to use. Now we can do our calculations. So we get our interval by doing x bar plus or minus T star times S sub x divided by square root of n, which is equal to negative 3.587 plus or minus 2.704 times 2.506 divided by square root of 47. And that creates an interval. We do these two calculations from negative 4.575 to negative 2.59. And that's our interval. So right here, this is our 99% confidence interval. Now that we've done the math, we move on to the last step in our 4-step process, and that's the conclusion. And we conclude that we are 99% confident that the interval from negative 4.575 to negative 2.599 captures the true mean, let me get my context right, change in BMC for breastfeeding mothers. So again, that conclusion statement is what wraps it all up. That connects everything back to the context, and it's the actual like answer, so to say. So anything I can clarify? So part B here says, based on your interval from part A, do these data give good evidence that on the average nursing mothers lose bone mineral? Explain. All right, so in this case, since all the plausible values are negative, which indicates bone loss, the data give convincing evidence that breastfeeding mothers lose bone minerals on average. And so that's how this interval supports that claim. Right? There's no plausible value that says that there isn't bone loss. So we have really strong evidence to say that on average there is. Is there anything I can clarify? So we'll go to our last example here. Right? High school students who take the SAT math exam a second time generally score higher than on their first try. Past data suggests that the score increase has a standard deviation of about 50 points. How large a sample of high school students would be needed to estimate the mean change in SAT score within 2 points with 95% confidence? We want to show our work. Right, so again, we're going to be solving this inequality for n. So I'm going to start just by listing what we have and what we need. Right. We want a 95% confidence, and using table A, we know that the z star that goes along with 95% confidence is 1.96. We have a standard deviation from previous results of 50 points. We don't know n. The target margin of error is 2 points. So now we're going to replace everything. Z star is 1.96. Sigma is 50 divided by square root of n. It's less than or equal to 2. We need to rearrange this to solve for n. And so we're going to multiply each side by the square root of n, and then divide each side by 2. That will cancel the square root of n from the left-hand side, and cancel the 2 from the right-hand side. So we get 1.96 times 50 divided by 2 is less than or equal to square root of n. We square both sides. That cancels out my square root. Right? We punch this whole thing on the left-hand side through a calculator, and we will get 2,401 is less than or equal to n. Right? We don't have a decimal in this case, which is kind of nice. We hit on or right on a whole number, which means we can actually use that value. So we can conclude that we would need at least 2,401 high school students to estimate the mean change in SAT score to within 2 points with 95% confidence. And we've answered our question. And again, I'm writing out these statements and things to demonstrate that the math itself is only part of the solution. It's not considered a complete answer if all you do is provide n is greater than or equal to 2,401, right? We need to give a statement at the end and say, this is what this number actually implies. Is there any questions or anything I can clarify? All right, so with that, that's the presentation and the examples for today. As we've been doing, tomorrow will be for more practice. I haven't decided if I'm doing a Desmos activity or a Paradox activity. It's going to be one of those most likely, or I'll come up with something else, I don't know. And we'll do some practice problems. We'll, get a little more comfortable with these concepts. And then, this is the last week for Chapter 8. Move on to Chapter 9 next week. The assessments for Chapter 8 are almost ready. I think I published the multiple choice assessment, and I am hoping to have the free response questions published and ready, that assignment ready later today, maybe. However, don't worry about those yet. Right? We're going to still finish up with tomorrow, answer any questions, be able to start working on those assessments later this week if you can. Other than that, if you have any other questions, you need help on anything else we've covered so far, this lesson, previous lessons, previous assessments, please stick around. You can talk to me about it, let me know. I can give you help, or you can send me a message. And if not, then I will see you tomorrow for more practice on section 8.3. Have an enjoyable rest of your day.